orogeny. Other examples you find in the video referenced in the description below. The 5 tutorials are designed to introduce geoscientists, teachers and students how to reconstruct with BlenderGIS complex geological structures in virtual reality. First tutorial is about projecting geological data onto digital elevation models and is referenced in the description below. During this second tutorial we learn one way how to place cross-sections and to carry out geological mapping on digital elevation models. Let's start with the cross-section, scaled to match the digital elevation model. I assume you have installed the two add-ons, BlenderGIS and Import Images as Planes. I will use the cross-sections in PNG formats taken from the sources listed in this slide. In this second slide I have summarized the procedures we will go through now. Before you add the cross-section, mark on the DM the profile trace and mark the profile endpoints as shown here in red. Change the transformation orientation to local and place the cursor at one of the profile endpoints. Go to Add, press on Image and select Image as Planes. Locate your cross-section, select and press Import Images as Planes. We'll probably not see the cross-section yet, hence go to Object, press Snap and choose the option Select to Cursor and scale up the cross-section. Note that the center of your cross-section is at the cursor position at the endpoint of your profile trace. Select the profile in object mode and move the cross-section start point to the endpoint of the profile trace. Move the cross-section until the 2 points coincide. Now, very important, change the transformation pivot point to 3D cursor. You will notice the pivot handle snap to the cursor position. Herewith we make sure that transformations are made now with reference to the cursor located at the endpoint of the profile trace. I rotated the cross-section around the vertical axis into the profile trace and will scale it now. I scale the cross-section using the white circle. Herewith the height and the width are scaled with the same ratio. This I do because my cross-section has no vertical acceleration. I verify now that the depth scale matches by comparing the 0 meter depth of the cross-section coincides with the 0 meter datum of the DEM. If the height scale of the cross-section does not match, then snap the cursor now to the 0 meter datum level of the DEM and scale the cross-section in the local height direction, in my case the Y direction, until the surface line of the cross-section coincides with the DEM. Et voila, the cross-section is now correctly placed. The second cross-section I have placed with matching the XYZ coordinates given on the cross-section with the DEM coordinate points. How to find coordinate points on the DEM is explained in tutorial part 1. The second topic of this video is about mapping geological units onto a DEM. The procedure is again summarized in a slide. Select your DEM and change to Edit mode and select Edge mode. Pick up the knife and outline the boundaries of the geological unit according to your field observations. In edit mode, click Edit box and choose Circle box. Select the mesh of the geological unit. Go to Material Properties and select the color belonging to this geological unit and press Assign. If detailed field observation shall be brought onto the DEM, display a high-resolution landscape DEM and use it as a guide to trace the field situation onto your geological DEM. In this case, I outlined the basal carbonate unit of the Upper Jurassic limestone cliff. An end product of the geological mapping could look like this. Reading the geological field information calls for major deformation. The southern part of the fold is thrusted onto the northern fold lip. The thrust is mapped in 3D and shown as a red displacement zone. This leads to the tutorial part 3, where I will show how true 3D thrust and fold construction can be done in BlenderGeologist. Jura Mountain offers here excellent training ground. In this thrust and fold belt you can find thrusts, fold thrusts and normal folds that pre-exist the compression of folding and thrusting. During thrusting and folding the normal folds remain inactive or were reactivated. To reconstruct the different folds and thrust, we will use simple animation of possible deformation processes to model the geometric end results. The resulting deformation models of these different working hypotheses could help to interpret complex geological situations observed in the field. I hope you find the tutorials useful. Please let me know of any improvement possibilities. Thank you for subscribing to my channel and give me a thumbs up if warranted. Thank you.